shared memory programming model process interact through shared memory. And explicit synchronization mechanisms such as locks or barrier semaphores, where you develop shared objects in an object-oriented environment such as Java in form of like synchronized monitors. And another family of parallel programming models is so-called distributed memory programming models or message passing, where there is no shared memory. So therefore, the way how processes interact, they interact by sending messages to each other. Otherwise, you implement higher level or more abstract mechanisms such as remote method invocation or remote procedure calling on top of message passing. And of course, there is a synchronization which is involved, which is implicit because message to be received should be sent. So therefore, receive is typically a blocking call. It blocks until something arrives. Some synchronization mechanism, because most of time in this course we will devote to shared memory programming with multiple threads. To synchronize threads and to coordinate access to shared memory, you might be using locks, condition variables. Who knows what condition variable is? It's in the pthread context, and also in Java, by the way, as well. Wait set. Okay, 1/3 of you. Okay, barriers, which is a collective synchronization. The threads are waiting at the barrier, all of them to arrive, and when all of them have arrived at the barrier, they can proceed. So semaphores, which can be used as combination of lock condition variables. Monitors, which are synchronized objects, concurrent objects, which can be even lock-free objects. Based on this compare and swap or compare and set instruction, which is now you can find it in instruction set of any modern CPUs. COS instruction, which is very powerful instruction, just pay attention to it. Compare and swap. So it takes three parameters. First, old value to compare against in the memory location, and if it's equal, to replace with a new value. If it's not equal, then it has no effect. But it returns whether it's successful or not. You can branch on it. Whether COS really has done it or it was not done, and you can branch after that. Why it's so powerful? Because I can give you like a homework, if you will, just even in advance, even though that you might not have enough knowledge. So there is so-called wait-free consensus problem. You know, consensus, when you have multiple processes, they should agree on something, right? There's consensus problem. Assume that they should agree on a common value, like meeting time, for example. And the protocol is that you need to develop a solution that they will agree on a value which is proposed first. Okay? So that means that each process thread, I have several of them, they have own value, my value. Each thread has my value, right? And there is a common value, common. So each thread at some point it calls propose, like my value common into common, right? And then it might call read, like read common. And here propose my value. So a thread is doing it sometime. It's not synchronous invocation, right? Anytime. But the most important that after it reads common, all of them, they should read the same common value, which was proposed first. Why it's called wait-free consensus? Imagine that this thread proposes first my value. It reads its value because it was proposed first, right? It doesn't need to wait others. It just can go because the algorithm should ensure that others also will read that value. Okay? So therefore threads, they don't really need to wait for each other. They just propose, take the value and leave. And they should get the same value, all of them. Okay? Now, this problem is called weight-free consensus problem, was used as some kind of benchmark for synchronization mechanisms such as locks, condition variables, barriers, and so forth, for how many processes you can solve this problem in weight-free fashion, being weight-free. Okay? Now, I can give you results. Locks, only for 2 processes, weight-free. Of course, you can solve for more than 2, but not weight-free. Okay? This combination locks with condition variables, the same story, only for 2. Semaphores, only for 2. Okay, barriers is combination locks and condition variables, actually, in fact. Then also such operations like so-called 2-op operation. It's atomic memory operation. For example, test and set, or swap, which is guaranteed by hardware to be atomic, to swap value in location with a register like this, right, in one hop. Also only for 2 processes. Weight-free. And only this one allows to solve for any number of processes, very scalable. So therefore, if you can come up with some kind of pseudocode how to use this instruction to solve this consensus-free problem, send me solution. Don't look at on the web. And I can give you 1 extra bonus for that. Okay. Now, transactional memory, which is hardware-supported transactional memory nowadays, allows you to also achieve some kind of transactional style of execution. The transaction means all or nothing, right, against shared state or shared memory. Now, when you create a parallel program, I said create or write. Usually, a programmer passes through 4 steps. Okay, not necessarily, but it's like in common case. So first step, that maybe that's how our brain works. First we think about sequentially, right? Sequential. That's what you think when you develop an algorithm from scratch, given some problem. Typically you think it's like a workflow, one single threaded, like sequential execution. Then you might look at what are tasks while executing sequentially, solving this problem. These are tasks. And then you see some tasks, they are like independent. And that's where potential parallelism is. Okay? So you discover it. And then you discover these tasks. Then you assign them to threads or processes. You start creating threads as a pool of threads. Or you create whenever it's needed. And then you have a parallel program. Of course, you need to orchestrate how this process interact. That's where the synchronization comes in place if you have a shared memory. Otherwise, you develop messaging system. What messages, how they're sent. Then you have finally parallel program which should be executed on some platform, and then there is a mapping of process to threads, and that's typically is done by operating system. You rely on it, right? And the bad news is that unfortunately there is no yet parallelizing compiler good enough to do that automatically to develop parallel programs, given sequential one. Okay, that's a challenge, and probably this still open problem, of course, and I don't believe that it will be solved. So therefore, some people believe that parallel programming is the art. Okay? But still, I will show you some paradigms of parallel execution, which are general enough that you can find in many, many problems, And as soon as you have this collection of paradigms, you can apply them or combine them to develop parallel program. Of course, we can look at slides devoted to each step. So decomposition is a break up computation into tasks if you program in terms of tasks. But this is a matter of taste. So I prefer to do it in this way. So tasks which are like loop iterations, for example, or function calls, or some fragments, tasks. Task might become available dynamically, not necessarily statically. And the number of also available tasks can vary because new tasks might be generated. And then you need to identify concurrency to decide how tasks depend on each other. It's like iterations. Do they depend on each other in a loop? Can you do something about it to make them independent and do parallel for instead of for? Something like this. Okay? And then, of course, the major design issue here is granularity of a task. Okay? Fine-grained or coarse-grained to keep your cores busy, and of course you probably need to know your target platform. Right? So the simplest way to identify concurrency to look at loops. Okay? So if you have a for loop, that means that this loop knows how many times it's going to iterate. Okay? Unless you have some conditional if something break out. Right? But still for identifies loop boundaries. So in this case, you should look at iterations. Are they independent? If so, in OpenMP, you can just simply say parallel for pragma in front of it. Okay? And they will be executed, iterations will be executed in parallel threads concurrently. Okay? If it's while loop, then we create something like bag of tasks. That each iteration look at some like shared bag of tasks, whatever it is. It could be set or it could be even just shared integer. Grab the task from it, executes, right, and put results somewhere, maybe in another shared variable. Furthermore, the thread, when it executes a task, it might create another task, okay, which it can either keep on its own or can put it in a bag, right? So that's how you can deal with while loops. So you can actually parallelize iterative computations or even recursive computations, I will show you, given that these iterations or recursive calls are independent. And typically, the basic idea here of independency is divide and conquer. It's like you have data domain you need to iterate over. You divide your domain on chunks, right, or blocks or stripes or strips, how you prefer to call them. Assign workers to work on these subdomains to work in parallel. But if there is no enough concurrency in loops, then maybe you should look at the algorithm. Maybe there are stages, right? And it might happen that these stages might also execute concurrently, or you can organize them in some kind of pipeline. Okay, now it sounds a bit abstract, but I'm going to give you this set of paradigms. Assignment is how you divide this work that you defined in form of tasks among threads. Like static assignment, parallel for I mentioned, or dynamic, bag of tasks, right? Furthermore, you can also rely on runtime system to assign tasks, like in OpenMP task support. You just specify a number of threads and then start saying that this fragment is a task, and runtime system will create tasks, even in, like you might have a loop, and within a loop, iteration is a task. And it will assign tasks to threads dynamically, to pool of threads. And that threads will be allocated to cores to run. It may happen that one thread in a pool has a lot of work to do, another one doesn't have. So then your runtime, it's not, you're not really programming this, okay? It's in runtime, it's like included. Work did and work still in, like in runtime of OpenMP. So orchestration, when you decide, are you going for shared memory for message passing? between threads, or maybe you make a decision earlier, but you need to orchestrate these parallel activities. If it's shared memory, you pick up synchronization mechanisms. And this is actually a matter of taste. Okay? For example, you can achieve the same powerfulness, expressiveness, using semaphores versus locks and conditional variables. Okay? I wouldn't recommend you to intermix locks, conditional variables, and semaphores in one application. You choose. Either you go with semaphores or you stay with locks, conditional variables, for example. Okay? If you are in an object-oriented environment, then you go for shared objects, right, which can be synchronized. Only one thread can access object at a time, so-called monitor model, or you can allow simultaneous access, like different methods can be invoked simultaneously. This is really concurrent objects. Okay? This orchestration. Mapping is when you have parallel program, how you map it to available resources, right? Of course, it depends on platform where it should be executed, and typically you rely on operating system. You don't really have full control on it. And your homework assignments you'll be doing on your laptops, I believe, but some of homework assignments require to do performance evaluation. It's execution time versus number of threads. Okay? When you increase number of threads, you increase parallelism, you expect that you will get some speed up. Execution time should decrease, right? But because I don't believe that your laptops have more than 4 cores, maybe I don't know, then I would recommend you to go to this shell servers like Avril and others. I still couldn't discover where they are. I know that one of them, it's called avril.sys.kth.sa, but I will try to find it before first homework is due. And then you can do SSH to those servers, move your program there, and run there, because all the servers, they have up to 32 cores. Of course, there might be other people there. It's not clean environment, but nevertheless. You can get some speed up, you will see. By the way, how to move program, copy paste. Okay? Cat, you know cat? Utility in Linux? You say cat myprogram.c, and then you copy from laptop, put it in there. That's how you move it. Copy paste. By the way, if you have any problem with this, don't be shy. Don't hesitate asking either me or TA, Edward. Okay? Because I could imagine some of you are beginners, and you might spend a long time just solving very small thing which can be answered within a minute. Okay. Now, these are helping slides that just to show you, because I'm not going to use specific language unless I give you a tutorial. Like for pthreads, I'll be using C, for the shared objects, Java. But in examples, I will be using hypothetical language, which is very similar to C. And there will be duality between these languages in OpenMP dialect of C. So it's very similar to C. So I'll be using like declaration with some types, integers and characters and so forth, arrays. Right? So I will be using this keyword process to declare detached thread or process. So within a process, I can define some shared variables which are private within this process. It's like a parallel pragma in OpenMP. Then statements, I'll be using just assignment statement is clear. Control flow statements like conditional if, loops, while and for, just like in C, okay, with some quantifiers. So sometimes you might see this st means such that. It's like from I from 1 till n such that I not equal x. By 2 means from 1 till n, like 2, 3, and so forth, odd numbers. But I hope you can read these examples, because even though that we will be they will illustrate some conceptual things like paradigms, but they're rather simple. Okay? But if you will have any problem, ask me. This comes parallel dialect of this language. Okay, concurrent statement. Core stands for concurrent, then execute something in parallel, and to C, it's end of statement, because it's a statement. So we need begin and end, right, of it. And what is in the between is something to be executed concurrently. Okay? This is exactly parallel region in OpenMP. Okay? If any of you familiar, or you will see later. Await statement, which is general statement, I claim, to indicate any type of synchronization, mutual exclusion, condition synchronization. Await. I will introduce it later. Now, about core statement, as I mentioned, it's a parallel statement. Something before core, something after. Okay? This is like sequential. Now it's core here. It's parallel. So what is executed is this S1 till Sn in parallel threads. Different code. Okay? So therefore we need somehow to distinguish with these vertical lines. So end of parallel statement, it means that all these threads complete, and after that Sn plus 1 is executed. Is it clear? So n thread they are running, when all of them complete there is some kind of implicit barrier here, or C. So then Sn plus 1, because this is a statement. And this picture illustrates what's happening. Control flow. If all threads should execute the same code but parameterized, in this case you can say core with a quantifier, saying that they're going to be n by n threads, n square threads, and each thread will be executing this code S, but with different parameters I and j, right? So the first thread will take 1, 1, I is equal 1, j is equal 1. The next one will take 1, 2, 1, 3, up to 1 n, then 2, 1, and so forth. Is it clear? N by n threads, each thread gets, is the same like parallel region with parallel progeny in OpenMP with private I and j. So that's illustration here. But I'm not using OpenMP. I don't want to mix up with C because some of you might not know. So therefore I'm using this hypothetical language, which is actually was developed even in Arizona State University by Gregory Andrews that I used before. And it's happened that I know him personally. Okay, he's like friend of mine. But it's not because he's friend I'm using it, because I really found that it's quite easy to read this text. Process declaration, it will be like process, you can give a name to it, even you create a ref process with some quantifier here, and there is a text of process here, a program to be executed, and within here you can also declare some variables, but in this case these variables are private to that process. Now it comes the interesting stuff about programming paradigms. These are like basic type of parallelism that you can find in quite many applications. First, it's iterative parallelism. Parallelism of independent iterations. Those iterations that do not depend on each other and they can be executed in parallel threads. Recursive parallelism is quite similar, but in this case you have a function recursive, you call it on some domain or some problem, and this function decides, okay, let it split on two subproblems, two subdomains, and call itself twice, more than once. And these two invocations might be independent because they work on different domains or subproblems, right? Why not to execute them in parallel threads? There's the idea of recursive parallelism, of parallelism of independent recursive calls. So both of them, they're based on this idea of divide and conquer. Something like data domain or problem is divided on subdomains or subproblems, and then you have iterations that iterate on different data in parallel, and they have recursive calls that also operate on different data doing independent actions. So this one is also general enough, producer consumer or pipeline. So producer consumer is also pipeline, but it has only two stages. Producer that produces some values and consumer that consumes them, okay, and process them. Otherwise, if you have several stages, so then it really pipeline, so that each stage consumes something from the previous stage, if any, and produce something for the next stage, if any. This is so-called data flow computational style, which is nowadays is quite famous, becomes in big data analytics tools. Client servers. Okay, this paradigm is mostly for distributed programming, right, distributed computing, where you have two types of processes which are distinguished how do they behave. Client is proactive, right? So it initiates communication, so it sends first, right, like request. And the server is reactive. So it waits for request to come and then it replies. So it does not really initiate anything on its own. It's reactive. That's client-server interaction. And of course, server could be multi-threaded to service multiple clients in separate threads, right? And if it's happened that the threads access shared resource like shared database, you need to synchronize them. But how that's in this way you improve throughput of a server to be able to service multiple clients in separate threads. But another type of parallelism here, you have a client is doing something and server is doing something. It means that they coexist simultaneously, being alive. Interacting peers, where you build the application of peers, which are somewhat equal in terms of set of algorithms they perform, how do they behave, and what do they do. So a peer can be both server and client at the same time, right? Server means provide some service to other peers and also request service from other peers. Therefore, they are somewhat indistinguishable. And furthermore, peers might also serve as a router of messages directed from one peer to another, because it might not necessarily that peers, they are fully directed to each other, right? So therefore, peer, typically, it's at the same time server, client, and router, okay, at the same time. Therefore, you could imagine that it should have like 3 threads in it, right? One is proactive thread, like a client. Another is reactive, react to provide something that if other client is asking, other peer is asking, and also as a router to route messages. Okay, let's look at through one by one. So iterative parallelism is parallelism of independent iterations, right? And quite many problems, they have this iterative computation style, right? Iterate. To examine data, to compute results, and these loops that applications might have can be parallelized. Not all of them, but some of them. Those where iterations do not depend on each other. But if you see that the next iteration can start only when the previous completes, because it uses result of the previous one, of course you cannot parallelize them, right? Because there is true dependency between next iteration and previous one. So the next should wait until previous completes. But you can break this type, maybe modifying loop, if possible. It depends on algorithm what you are doing, what the loop is doing. Okay, let's look at this example, which exposes exhaustive like parallelism. Matrix multiplication, if you remember how to multiply matrices. If you remember how to do that. Okay, let me also recall myself. So imagine we have, just for simplicity, matrices n by n, right? And what you do, you take a row from one matrix, okay, I. Do you see what I'm drawing here? Is it visible? Okay. Otherwise, just complain if it's not. So there is J here, column, vector. And then what you do, you multiply these elements one by one, right? Like this way. And you sum them up. So eventually you get one point, so-called dot product, okay? One element of resulting matrix. Let's say this is A, this is B, like it's on the slide, and you compute C, and this is Cij, one value, dot product. You multiply this vector to this one. Okay? That's matrix multiplication. And to see this, to compute Cij, you need to read this. A is not modified. You need to read this. B is not modified. But eventually, you need to write Cij. If someone is computing Ci plus 1j, so that computation is independent from this one, right? Again, you need to read two vectors, multiply them, and write in some point. That's why this problem really has a lot of parallelism in it, potential parallelism. But of course, you need to see it. So this is sequential version. Okay, this is matrix A, n by n, matrix B, n by n. This is resulting matrix. So assume that these two matrices are given. And then we have loop over rows. Inside, you have inner loop over columns. Cij initially 0. And this is loop to compute dot product. Cij. I don't know how do you like to read source code or not, but I've been reading source code a lot in my life in different languages. Sometimes it's really boring, right? But hopefully you will get this, okay? This sequential program. Now, as we say that, let's look at this loop, 4 over I, okay? So each iteration, what does it compute, each iteration? It computes a row of resulting matrix where I is fixed, right? One row. Right? First iteration, when I equal 1, it will compute C1, 1, C1, 2, and so forth. Resulting matrix, one row of it. Okay? So another iteration will compute second row. So this iteration is independent. Why not to replace 4 with a core? That's what I do. So instead of 4 statement over here, I put core statement, the one that I just introduced. Okay? So for this core statement, it will create n threads. Okay? Each thread will be executing this loop, but for different values of I. I is private. Okay? So first thread will be executing I equals 0. It will compute 0th row of resulting matrix. Next thread, first row. The next thread, second row, and so forth. And we can claim and prove, if you will, or maybe you see intuitively, that these threads are independent because they read A and B, but they write different data in C, right? Different places. Okay? That's why they're independent. Now you already start maybe understanding that to be independent, threads can read some shared data, but they should write different data, right? Shared data. It means that write set should be disjoint between threads. In this case, they're independent. Okay, now, if you look at this for loop, in a similar way, you can discover that it's also independent. Okay? Therefore, maybe instead of replacing this for, we can replace these two fors with such core statement, with two quantifiers, I from 0 to n plus minus 1, j from 0 to n minus 1. Okay? In this case, we will have n by n threads with different values of I and j. Okay? So each thread will be responsible to compute one dot product. It will be reading corresponding row from A, corresponding column from J, and compute one value. Okay? And there will be n by n such threads. So therefore, you just replace this one, 2/4 with core. Okay, that's in iterative parallelism illustrated with matrix multiplication. And in your homework number 1, when you should supposed to program with p-threads, I have given you a program that computes sum of matrix elements, not multiply, but summation. Okay. Just look at it. Of course, maybe after tutorial on p-threads, right? Or some of you already know p-threads, as I understand, and you need to modify it. Therefore, I strongly recommend you to do the first homework, first task. Okay. Any questions here? Okay, let's start.
Is it possible for the task to be too small so that the overhead to make threads is
yes,
greater than
yes, of course, yes. Because here is the inner loop. Of course, I haven't discussed this loop, but this loop you see that on the right-hand side you have Cij, and on the left-hand side, so the iterations are not independent, right? Because typically this, if you do such an aggregate like summations, so you cannot do that. And as I mentioned, the design issue typically as programmer, you choose what is granularity of tasks. They may be so small, teeny. For example, in one of these homeworks, problems of first homework, I don't remember which one, I think it's the first one, you need to develop bag of tasks, right, implement. And if your matrix is very small, and granularity of tasks just like, and you create like 10 threads, for example, for matrix, let's say 10 by 10, or even 100 by 100. So pthread creates one thread. So to create 10 of them, you need to put it in a loop 10 times. As soon as one thread is created, it's already start executing, right? So while this for loop keep creating, the first worker, which is alive, in bag of tasks, it will execute everything. And when another worker created, bag of tasks is empty. Everything is done. Why? Because granularity of task was very small, right? So you don't really gain anything creating 10 threads because it's executed by one of them. It actually was sequential execution. So therefore, granularity of task is very important for performance. Okay? And overhead of could be much bigger, as I said, like creating the threads than tasks. Okay? But of course, if you have millions of tasks, if it happens, then it might make sense to have them even small. Here, it was task on the level of rows. Here is task on the level of one element, right? Now, let's go for the next one, recursive parallelism. So recursive parallelism is it's the same story, divide and conquer, but it's parallelism of independent recursive calls. So assume that you have a recursive function and it calls itself inside more than once. Why? Because it decided, okay, let's there's some conditional there, like convergence, and it says, or termination condition saying that, okay, this is domain is too big, let's divide it on 2 subdomains and call itself twice on these 2 subdomains. And because it works on different data, these 2 calls are independent. They can be executed in parallel threads. Actually, you can keep one task in the thread which is called. You don't need to create, but you can create extra thread to execute another task. Okay? Divide and conquer this. There are different examples which I give also as a homework, quick sort in particular. And this one, adaptive quadrature, it also compute pi task in homework. Let's look at this one, adaptive quadrature. So adaptive quadrature, what you need to do here, you need to do approximation of integral of some function f of x from a to b on this interval. So you need to compute this. Because imagine that you cannot take it analytically, you compute it, right? And of course it's approximation, so it's not exact value. So you need to compute this area. This area is this one, which is in gray shape, under the function and between A and B. Is it clear? Now, so this is a sequential, like classical way of doing that you split this interval A to B on subintervals, number of intervals, and I is specified. It's like command line parameter, you can put it, right? So the more intervals you have, the more computation you need to do, but maybe you get more precise value. Okay, subintervals, and for each this subinterval delta x, you compute this square of this trapezoid, okay? Using Euclid geometry from high school, if you remember. And then you need to sum them up, and then it gives you area. That's a sequential. You can look at it if it's too short time just to understand what it does, but you trust me, so it does according to this picture. For loop and so on. But imagine that this curve can have different shape. It might have also some kind of flat shape like this. So therefore, maybe this type of execution is not good enough to approximate. So therefore, it was suggested another one, which is called recursive adaptive quadrature procedure. So it goes through approximations, first, second, and so forth, until it reaches the one that is good enough, given some tolerance epsilon error, right, between the previous iteration and the next one. So the first approximation is just this area, you see, from A to B, f of A, f of B. According to geometric, how to compute this trapezoid area, it's f of A plus f of B divided by 2 multiplied by B minus A. If anyone remember from Skyfire, how to compute it. Okay? That's first. Now, let's split this A to B on 2 equal subintervals. This intermediate point B minus A divided by 2, M here. So we compute L left-hand side area, R right-hand side area from A to M, and this one from M to B. Okay? Then we sum them up together. We have better approximation. You see that, right? It's quite obvious to see that it's better. And then we compare them against each other just by subtracting and taking absolute value and see whether it's within tolerance epsilon or not. If we converged or not. Shall we continue, or maybe data are not changing any longer results, so probably we can stop. So if you implement this as a function, you call first function from A to B, okay? So then you divide A to B with the intermediate point, and you call the same function, but with parameters A to M, and another call from M to B, 2 calls. When they return, you take the results, you sum them up, and compute. That's the idea of recursion parallelism here. And these 2 calls to compute left-hand side and right-hand side area, they're independent. Okay? And here comes a sequential program, or this procedure. Actually, it's implemented as a function that returns double. It takes these 5 parameters. Left-hand side boundary, initially it's A, right? This is how you call it. Right-hand side, it's B. F of L, F of A. These are when you call it, right? These are like actual parameters. F of B. And this area, which is pre-computed, like first approximation. This you call it first time. And then what it does, it computes M in between F of M, left-hand side area, right-hand side area. Then it compares this against first approximation. If it's more than epsilon, we cannot really tolerate this error, difference between them. Then we call quad twice, but on with different parameters. L till M, right? And M till R. And of course we need to wait when they return. This one returns left area, this is right area, and then we return it as a result. Of course, each of these calls also can split, right? When it executes this if statement. You don't really know how far this recursion will go. How many calls will. It depends on shape of the curve and this epsilon also. That's the one. But the most essential that these two calls are independent. So therefore what you can do, you can again use call statement saying, it's not shown, here it is, saying that this will be executed in one thread, this will be executed in another thread. So in fact, this quad will be executed in this thread, right? Or maybe this one. It's not necessarily that you have master thread and then you create two child threads to execute these calls. Master can take one of the jobs, right? And wait when child complete. Is it clear? So this adaptive quadrature is supposed to implement in problem to compute pi, or p, how you call it. 3.15 and so forth. That's constant. Magic constant from circle. Okay, now I'm again out of time. So produce consumer, next time we go for it. Okay. But lecture 3 is very short, that's why eventually I will synchronize, I think, after that. I really appreciate your attention, but now it's 5 o'clock, so you're free to go.